In the last homework that you did, you explored various relationships between gas variables and the outcome. What I'm going to do now is explain what you should have seen in the experiments and give you some equations that go along with those relationships. These equations are collectively known as gas laws. First gas law that I'd like to talk about is Boyle's law. And Boyle's law states that pressure will increase if volume decreases. And the important caveat to this is it has to be at constant temperature. You would use Boyle's law, this relationship between the two, if you wanted to calculate what the pressure would be if you changed the volume of a gas in an expandable container. The equation for that looks like this. The initial pressure, or P1, and the first volume, or initial volume, V1, is equal to P2 V2. And so if you had a problem that said balloon at a volume of 6 liters and 1 atm of pressure is put in a vacuum and pressure decreases to half an atm, what's the new volume? So you'd put your variables into the equation. The initial pressure is 1 atm. The initial volume is 6 liters. The pressure goes down to 0.5 atm, because if you're in a vacuum, it's like a little bell jar, and I put a balloon in here, and I take air molecules out of the vacuum. That's how a vacuum works. The outside pressure equals 5 atms. Inside of the balloon, the volume will expand until the pressure on the inside is equal to the pressure on the outside. So that's why we can set it equal here. Times V2. And then you solve, and the volume will equal 12 liters. And that makes sense. Pressure increases, volume decreases, or vice versa. So here my pressure is decreasing, so my volume should increase. Second gas law, Charles' law. Charles' law looks at the relationship between temperature and volume, and they are directly proportional. And this is at a constant pressure. So if you increase temperature, volume will increase. If you decrease temperature, volume will decrease. If we think about that on a molecular level, you have a balloon, because the volume is changing. You have molecules that are moving around. And their molecular motion is determined by their energy. And the energy is measured by temperature. That's what heat is, kinetic molecular movement. So if you decrease the energy of these molecules inside of the balloon, they'll exert a lower force on the walls of the balloon, and thus the balloon will shrink. Again, has to do with a balance of forces when you have an expandable container. The outside of the balloon is 1 atm, that's our measure of force. If you decrease the temperature of the balloon, it will decrease in size until the pressure is once again equal to the outside pressure. So essentially what you're doing is decreasing the volume and increasing the interior pressure. So our equation for that looks like this. V1 over T1 equals V2 over T2 at a constant pressure. So let's say we had this problem, a balloon with a volume of 10 liters at a temperature of 395, which is room temp, because we always use Kelvin. If temperature is increased to 450, what is the volume? So we use our equation. V1 is 10 liters, T1 is 395, X liters, that's what we're looking for, over 450. And if you do your math, you'll get 11.4 liters. And then we do a logic check and say temperature increased, volume should increase. And we see that that has happened. Let's look now at Gay-Lussac's law. This is the relationship between pressure and temp at a constant volume. Volume is determined by the container. So if it's in a non-expandable container, it's determined by the container that it's in. So if I had a gas in a steel canister with a pressure of 1 atm at room temperature, 395 Kelvin, what would happen if I heated the gas up? Well, these are directly proportional. So as one increases, so does the other, and vice versa. And the equation looks like this. P1 over T1 equals P2 over T2. And let's say it's heated up to 450 Kelvin. You should expect that the pressure will increase. Because the volume cannot change to maintain a constant pressure like we had in the last problem, the molecules will be moving faster and hitting the walls of the container with more force, increasing the pressure. Plug it into our equation here, 1 atm, 395 Kelvin, x atm, 450, we get 1.14 atm. There's one more law I'd like to talk about, Avogadro's law. Hopefully this name looks familiar to you. Based on Avogadro's work, we have Avogadro's number. And this number was actually derived from his discoveries of this next law. And what he found was that the volume of any gas at a constant pressure and temperature, so pressure constant and temperature constant, contains the same number of molecules. So if you had a balloon, and let's say it was 22.4 liters, this balloon would have 1 mole of gas. Doesn't matter what type of gas. 22.4 liters will contain 1 mole of gas. And the reason it doesn't matter is because under ideal conditions, the type of gas does not change the force exerted on the walls, and it doesn't change how temperature affects the gas. And because of that, the amount of molecules that have to be in a balloon to equal this amount is always 1 mole. This is where this number came from, because we know that 1 mole is 6.022 times 10 to the 23 molecules, or atoms, or particles, whatever. And so this gave rise to STP, which is standard temperature and pressure. So standard temperature and pressure states that at a temp equal to 273 Kelvin, which is 0 degrees Celsius, and a pressure equal to 1 atm, a gas that has a volume of 22.4 liters will contain 1 mole, always. And so this makes questions really easy at standard temperature pressure. So if I said to you, you have half a mole of hydrogen gas at STP, what's the volume? Well, we know 1 mole at STP is 22.4, so the volume would be 11.2 liters. But this is only at STP. If it's not standard temperature and pressure, has to be both of these, then we have to use something else, and we will do that next. So for now, you have an understanding of the relationship between pressure, volume, temperature, and we're starting to look at how moles of gas fits into that.